Okay. Wilson wasn't here yesterday. We'll see if he was paying attention. Wilson, do you remember what the key word was for this one? Jack said pert.
Continuous.
Okay, perfect. The key word here is continuous. If you hear the word continuous, we're going to use this one. If we just hear the word compounding, compounding is used on both of them. Without continuous, then we've got to use that one. Okay? The cool part about the continuous one is it's a nice compact form. It really works well. Okay? So when we're solving interest formulas, there may be times when we have to solve for t, and this is a really key idea, so make sure you're listening. Okay, because t is in the exponent. The only tool that we have right now in this class to deal with finding something that's missing in an exponent is just technology. In the next couple of years, you're going to learn about logarithms and stuff like that. Those will allow you to take an exponent up here and move it down where you can work with it. Okay, we don't have those yet. Those are pretty cool. Okay, so we're going to use technology in order to solve this. So here's the deal on this first problem. It says Susie received $500 for her birthday. You should know what letter that's going to represent. She put the money in a savings account earning 6.5% interest. You should know what letter that represents. Compounded monthly. Some key information right here. A whole bunch of stuff just got fed to us just by them saying compounded monthly. When will she have $750? Okay, there's a period right here, so let's deal with the formula first. Okay, Angela, are we going to use this one? Or are we going to use this one? The first one. What word's missing? What makes us use that one? Okay, they're not using the word continuous, and they did say compounding monthly. So that tells us that n equals 12 on this one, right? So the amount is going to be 500. Then it's going to be 1 plus whatever the interest rate is. So 0.065 divided by n, which is 12. And we don't know what the time is, so all we're going to do is we're going to take the n here and we're going to times it by t. So there's our formula. Yeah.
Could you replace the A with the 750 because that's what we're trying to accomplish?
You could, that's the idea, but the problem is we wouldn't have a tool to solve that with. Okay? So what we want the amount to be is 750. So we're going to do a little trick here. Instead of using A for this, we're going to put this in our calculator as Y1. And we're going to get a graph that grows like this. We're going to see the money go up and up and up and up. And D. What do we want it to be equal to? 750. So we're going to grab our calculator and we're going to put the two of these in here. And we're going to have the calculator help us solve this. Slide this off to the side here.
Do I have to look at accent for like T?
Yeah, you can put an X in for the T. So we're going to do 500 1 plus 0.065 divided by 12 because it's compounded monthly. And then that's going to be raised to the, I like putting the exponent in parentheses just to make sure that it does it right. That's going to be 12t, or in this case, 12x. There we go. Okay, and the second one's going to be 750. And everybody got those in there? Okay, we're definitely going to have to play with the window because if I just hit graph, I think I've got this in the standard window. This starts up here at $500 and then it just gets bigger from there. Okay, so I'm going to go to the window and I'm going to change the Y min and max. I'm going to go with 0 and I'm going to go up to 1,000 because that's going to fit the 500 and the 750 in there for sure. We can adjust it from there. These are just guesses. You don't have to do 0 and 1,000 if you don't want to. We just have to have a fit there. And we're counting this in months. This is negative 10 months to positive 10 months. So we don't need negative 10 months for sure. I am going to do a negative 2 there. You'll see why in just a second. Hopefully this works. And then I'm going to do 2 years. I'm going to do 24 months. Okay. Is this going to be a good window?
Yes.
We'll see. If it's not, the cool thing is we just make the calculator do it again. Worked out pretty well. Okay, decent window. In fact, 24 months is way too much. I mean, I might get a better picture if I came back here and just did maybe 12 months. Can somebody tell me why this is a gigantic, thick axis here? Mason.
It's because the little like grid markers.
Uh-huh.
Too big.
Yeah, I'm doing the Y scale of 1, so I'm putting a tick mark every one. I'm putting 1,000 tick marks on that vertical axis. So if I change that and I go to 100, it's going to look a little bit better. That starts at 500. There's the 750. You can see it's in between the 700 and the 800, and then they're going to cross right there. Can somebody raise their hand and remind us, how do I make the calculator find where they intersect? Smart, do you remember the buttons?
Is it second calc?
Second calc. And we want number 5. And it says first curve, that's the one for the account growing, the exponential right there. Second curve, that's the linear one that just stays steady at 750. If you want to take a guess, you can. If you don't want to, that's fine. So, which one's the answer? Angela. X is the answer. Can you say what that would mean? So that's 6.25 comma 750, right? So X is the answer. What does that mean? How would we say that in English?
After 6.25 months, she will have $750.
Perfect. Okay. $6.25 months. So it says, when will she have $750? 6.25 months. So let's take a look at the next part. And the next part kind of builds on what we talked about yesterday. There were some people asking some good questions and thinking this through. We're going to talk about something called effective rate. So here's what happens. When we compound things at different intervals, it actually has the effect of making the rate appear bigger than it actually is. So we saw yesterday an example where we got paid 9% for 40 years, and it worked out to be $3,600 in interest, $4,600 total. Okay, and then we compounded, we paid at different times, and we got a huge amount more. Okay, so the effect of that is it ends up paying us more effectively. So annual compounding, if it's 10%, it works out to be 10% per year. These are all yearly interest rates. If we compound it semi-annually, which would be twice a year, then it's going to bump the rate up to, effectively, it's going to be 10.25. So when banks advertise their savings rate, they usually advertise the effective rate, and if you watch, they'll say APY, or average annual percentage yield, or APR, annual percentage rate. They'll tell you this one because they want you to make it bigger. Okay, this is what the actual rate is. This is called a nominal rate, and this is the effective rate. And watch what happens here. If we compound annually, it's 10%. Compound semi-annually, 10.25%, and it just gets bigger and bigger and bigger. But like we talked about yesterday, the big impact is when you compound. Okay, going from compounding quarterly to compounding continuously doesn't make that big a difference. And compounding 365 times a year for daily hardly makes any difference at all if we change that to doing it every second and every millisecond and stuff like that. Okay, everybody good there? So let's talk about how they came up with this formula. Mason.
Is the interest, is the effective rate going to slowly curve like a limit?
Yeah. Yeah. So it starts out at 10% and then it goes to 10.517%. That's the most it could possibly be. That would be continuous. So we're not going to talk about the formula. We're going to talk about how they came up with the table. So here's the easiest way to find effective rate. You put $100 in and you put it in for 1 year. So they give you an interest rate. You say, hey, I'm just going to do $100 and I'm going to do it for 1 year. Okay. Anybody have an idea why we do $100? Why we don't do $1,000 or $10? Think about it for a second. Yeah.
Because $100 is 100%.
Very good. Exactly right. Because $100 is like 100%. So this is automatically going to be in like percents for us so we can compare these. So we're going to look at the following examples and we're going to figure out what is the effective rate for each one of these. So this is going to be 8% compounded quarterly for part A and 8% compounded continuously. So we're going to basically calculate these two lines for 8%. So here's what we do. Compounded quarterly, that means N is going to be 4. So we're going to put in $100. We're going to take the interest rate of 8%. We're going to divide it by 4. And then 4 times T. And what are we using for the time? 1 year. So continuous looks exactly the same, except for it's going to be $100. E raised to the 0.08 times 1. So we're going to throw those in the calculator. Okay, first question. Okay, did you get the same thing that I got? Mark.
On B, I got 100.33.
Oh, let's see. Oh, rounded? Oh, I see what I did. Yeah, 33. Thanks. Perfect. Thanks for catching that. Okay. I looked at the thousandths digits. Okay. Everybody got those numbers?
Yeah.
Glad we got that out of the way. Okay. Is everybody okay with me rounding at this point and writing dollars here? Okay. Are these the answers to the problem?
No.
Okay. Can somebody raise their hand and tell me what is the answer to this problem right here? If it says, what is the effective rate of 8% compounded quarterly? What is it? 8.24%. Raise your hand if you knew that. Okay, excellent. So do you see the value of having $100 in there just for 1 year? You just get to take off the 100 and any growth had to be whatever the percentage rate was. So this is going to be 8.33%. That would be pretty cool. If you have parents or grandparents, talk to them about interest rates in the 70s and 80s and stuff like that. And the interest rate market right now is kind of interesting as well. Okay, so last two problems.
That's funny.
Mason.
So the 8.34, we just divided what we got by our start, right?
No, you just take off the 100%. We started with 100, take off the 100, and whatever was left, the growth had to be due to the interest rate. Does that make sense? So just 100, yeah, subtract 100. Yeah, let me just write that down. Minus 100, minus 100. Everybody good there? Okay, so